In this video, we're going to take a look at Riemann sums and definite integrals. We're going to look more at what does it mean as we put more and more rectangles. So for example, this image that we have, you notice the blue rectangles, you have 1, 2, 3, 4, representing or approximating the area under the curve. Here with the magenta, we 1, 2, 3, 4, 5, 6, 7, 8, and then looks like we doubled that again and doubled that again, and as you get more and more rectangles in there, you can see that this yellow is an overestimate, but not nearly as a gross overestimate as the green. And the more and more that you add in there, the closer you'll get to the actual area under that curve. So first of all, let's take a look at definition of a Riemann sum. So here I have a part of the definition for Riemann sum. If you need to go ahead and pause the video to copy this down, go ahead and do that. I don't want you copying it down while we're talking about it. For this particular class, we're not going to go too deep into Riemann sums, but I want to make you aware of it because it's how we transfer this idea of these large summations into the idea of what an integral is and how powerful integration really is versus, these summation problems here. The partition, that is each, like for the rectangles, right, that is each rectangle that we're when we did LRAM, RRAM, the partition would be the each width of those rectangles, and this should look familiar too. That's a summation, right? And now we're going to get into summing functions themselves. Definition we're going to look at is the definition of definite integrals, and this is getting away from the idea of summation into the idea of integration, which is what we're going to really focus on in this chapter. The first part of this definition, again, if you need to pause the video, copy this stuff down. So right here, this is the limit. So this is a double absolute value. But really, that's why I wrote this over here. This represents just the change in x. So the way that it's written can be kind of confusing. But then right here, this b minus a over n should look familiar. That's if that's the a to b is the interval, the n is how many subintervals you're having. So that's then the regular partition would represent the length of each individual part in that partition. Takeaway here is that this idea of this limit summation here, and again this change in x, that just represents, hey, your rectangles are getting smaller and smaller and smaller and smaller. So you're adding, you have 10 rectangles that you're finding the area of, then you have 100 rectangles and 1,000. So you can't add, a million rectangles areas together. They're going to be infinitely small and smaller, and that's this as it approaches 0. So anyway, the cool thing is that this integral that we're going to learn about does that for us. It adds up an infinite number of rectangles for us, which is kind of amazing if you think about what it actually does. It's extremely powerful tool. So with continuity, continuity implies that a function can be integrated. The information that a function is continuous on a specific interval, then you know that it can be integrated. Continuous means that's when if you can trace the function without lifting your pen or pencil off the paper. So that includes corners and cusps, what else? Vertical tangents, horizontal tangents, all of those things that where there's a critical point, but there's not necessarily a max or min, right? All those things that we looked at before. So continuity implies that the function can be integrated. We're going to actually change the instructions of this one. We're not going to evaluate as the integral as a limit. Instead, what I want you to do is I want you to go ahead and graph the function y is equal to 2x, right? Because this is our function. Go ahead, take a minute and graph this. Something like this. And now take into consideration your limits. It says you're going from -2 to 1. And so we are going to go ahead and mark that on our graph. So right here's -2, and here's 1. Okay, and remember, the integral of something is just the area under the curve. That's bound to the x-axis. So from -2 to 0, you have that area, and then from 0 to 1, you have that area. And so now, go ahead and find the area of those two geometric shapes, which are triangles. Find the area of those two triangles. Found that the areas were, so I said a sub 1, that's the big purple one, that got 4. A sub 2 is the little one, that's 1. So here's the thing that you have to understand. If the area is beneath your x-axis, that is considered to be a negative area. If it's above, it's positive. So now when we combine those two together, the total area is -3. What you have to remember is if it's below the x-axis, you have to consider it to be a negative amount or negative value. If it's above, it's positive. So in this case, our answer is -3. What this definition states is it has to be continuous, of course, and basically when we find the area that's bound between the x-axis and the curve itself, that's what we consider the integral. And I'll draw a picture here. So let's say here, and our function looks something, let's say it looks something like this. Here's A, here's B. So if we were to find the area in here, right? Area under the curve bound by the x-axis and the curve, right there, that integral would look like this. From A to B, f of x, whatever that is, dx, or change in x. Okay, so then that's what that would look like. This would be dx. Same thing, but all right, so we're going to look at these are all common geometric shapes. So I want you to go ahead and graph all of these. Remember, this would be y equals 4, y equals x plus 2, and y equals the square root of 4 minus x squared. And we're only looking at the given intervals, 1 to 3, 0 to 3, and -2 to 2. You'll notice they are common geometric shapes. Go ahead and graph them and see if you can find the areas. Pause it, come back to the video when you're finished. You should have graphs that look something like this, and the purple is the area that we're asked to find, because looking at the limits, like on the first one, it's just from 1 to 3, gives us a rectangle there. So when we're looking at the area, it's going to be length times width, which is just 2 times 4. So that'd be 2 times 4, which is 8. So then that is 8 square units. Looking at the second one, you should notice that is a trapezoid, so the area is going to be a little bit different for the trapezoid. The way that I decided to do this one instead is to break it up into, whoops, that means do that, break it up into a rectangle and a triangle. So looking at the first one, you have an area for the triangle. You have 3 by 3, because this is 3 here, this is 3 here. So area of the triangle is going to be 3 times 3 times 1/2, which is 9 halves. And then the area of the rectangle is just going to be 3 times 2, which is 6. Then when you add those together, you end up with something like 21 halves. However, if you wanted to simplify that down, you could. And then on the last one, you have the area of a half circle. So the area of a half pi radius is 2 squared. And when you go through and simplify that down, that simplifies to 2 pi. Okay, so we're finding in these simple geometric figures, we can find the exact area under the curve. And so these next two properties are super important. Basically, oops, I wrote this one wrong. On this first one, if you integrate from one value to itself, that integral is always going to be 0. It's like you have your curve here, you're integrating from a to b, but a is just itself. So really there's just a straight line which has no area, and so that's why it's always 0. So you notice, if you notice your upper and lower limits are exactly the same, you know that your area is going to be 0, right? Straightforward, makes sense. On this next one, it's a little bit trickier. Look at your limits here. It goes from now b to a. So in this case, if b is over here, you're integrating that way. Okay, so your integral is backwards. So if you integrate backwards, that gives you a negative answer. Then everything above is negative, everything below is positive. However, you also notice that there is a negative out front. Okay, so if you have a negative, you can actually negate that those limits and actually flip those limits around. So negative integral b to a is a positive a to b. All right. So integrating backwards is a negative. So a negative negative will give you a positive. So that second one is kind of tricky to understand, but it's kind of like a double negative going on there. Okay, let's do these two and then we'll call it for this video. On this first one, thinking about those rules, go ahead and look at these rules here and go ahead and try these two on your own. See if you can figure out what they might be. On part B, look at this one. Oh, where's it at? Right here. We already did it. Okay, the x plus 2. So look at that one as you go through and answer that. So for the first one, when you integrate from a number to itself, remember that's always 0. So that makes sense. And then the second one, we already did this, right? We did from 0 to 3 of this function, x plus 2. It's not right. And that gave us the 21 over 2, and that's where I got this. So if I put a negative out front, I can flip those upper and lower limits, so it then becomes 0 to 3, and I know what my answer there is, 21 over 2, but now that negative makes this negative. Okay, so that's it for this video. When we come back, we'll continue on learning more about definite integrals.